老师这一课估计就不太结束了。12点课上多久？没上。没上是吧？没上，老师给大家讨论了。所以说。
你刚刚上那个？
没有。
哦。
他们说在 discussion。没上课。
之前那节是没上，我说你们是不是去上那个 verbal development？签什么到？要签什么？
人太少了。我肯定已经开始玩起来了。
Right, so I guess it's about that time. Right, so thanks to everyone for putting in your ideas to the Google form on what you thought made the good code good. And the idea really is to kind of crowdsource what you all think is the group and see what kind of things are the most important that you should consider from your perspective. We'll look at some other people's perspectives later, other groups as well, but we'll just see what you guys say. Okay, so what I've done is I've taken them all, I've kind of ranked them and put them into similar groups so we can kind of see them unless, and this is what we came up with. Can you read that okay at the back? Yeah? Okay, so, number one. We should read this in a reverse countdown, really. Okay, so number one, simple and easy to understand code. So you have 14 people said that. Perhaps not too surprising, but that's what as a group you thought was the most important, which I think is good. You also said that it should be well coded as well, so it should explain what the code is trying to do, why it's trying to do it. Always a good thing to communicate, not just to other developers, but to yourselves further on down the line. And you can remind yourself what you're trying to do, or were trying to do. Maintainable, the code should be definitely maintainable as well. So we had 7 responses that said that. So when it comes to fixed code, issues, etc., that shouldn't be too much of a big task. It should be something that's quite straightforward. A lot of people said the code should be efficient. We have a mention point on that, which we'll come back to later. It should follow good naming conventions. So when you're naming functions and variables, it should be self-explanatory what it is, as opposed to using A, B, C, or some random collection of characters. It should be concise, so code shouldn't be too long-winded or have too much in it. It should be sort of relatively straightforward and short. You shouldn't have too much unnecessary code gubbins in there. This was a good one, I thought. People said uses accepted code conventions. 5 people said that. So where you're using a language, if you're using something like a style guide for the language, that's a good thing. If you're working in a group of established developers who have their own established code conventions and guidelines, that's always a good idea, especially if you're coding with other people. It should be reusable. That's a very important point. Extensible as well, so you should be able to extend it to do other things. It shouldn't be too hard to do that. We'll come back to reusable again in a minute. I haven't seen this one before, and I think this is becoming more and more important. A few people said use static analysis tools to analyse your code. Now this is an interesting one, because there's a lot of static analysis code tools out there. There's JS Hints, I think, and there's also PyLinks, and you can run these tools over your code, your entire code base, and it'll give you an idea of the complexity of the code, a rough idea of, sort of how good the code is, the different values of good. I've had some success with using those tools. It should be modular as well, so it should be broken down. It shouldn't be just monolithic code. It should be broken down into separation of concerns. So using good decomposition into functions, libraries, and that also helps the usability, maintainability, readability, and extensibility. So modular is a very good one, I think, to focus on. Documentation. I was expecting a few more people to say documentation. But 3 people said documentation. That's a good one. So documenting the code, how it works, how other people can use it, how other people can extend it and develop the code. Very important. It should have a clear architecture so it's easy to see from the top down how everything fits together, well defined. I see a lot of code in my line of work which, let's just say, doesn't have a clear architecture. It's generally monolithic. It's difficult to extend. It's quite difficult to see what's going on, how the thing actually works. It should be tested as well to make sure that it's actually responding correctly to inputs that you're giving it, giving the correct outputs. It should also intend, and this, I haven't seen this one before, this is good, reduce dependencies. You shouldn't have too many dependencies in your code on other libraries where you don't really need them. I've seen a lot of people rush to get their code out and they think, I need this feature. Oh, that library has that feature. Whereas they've already using like 3 or 4 different libraries, and actually the feature was already in the libraries they were already using. I just wasn't aware of it. Code should be consistent. So if you're using this, I think, really is related to code conventions as well. So if you're using a certain style for writing your source code, making sure you maintain a consistency across that can be important. And as you work with other teams of developers, or within a team of developers, having that consistency can be quite important for clarity. And not just for conventions, but also for the way you attack various problems. So if someone's already come up with a solution for how to solve problem X, and you're using that solution slightly differently somewhere else, where you're using some variant of that solution, instead of recoding that solution yourself, have a look at what they've done, consider using their functions. And error checking as well. I've only put the ones in here which scored higher than 1. Error checking, yes, to make sure that your code provides some means to check itself when it's running, perhaps, and to give you some meaningful error messages when things go wrong. But there were some other interesting highlights, which some of which were quite bizarre and some quite amusing. One I thought was really good was code should be write once and read many. There's been a lot of studies that indicate that code is read far more times than it's ever written. So when you're coding, assume that it's going to be read a lot of times, either by yourself or by someone else. Don't reinvent the wheel. I see this a lot when I'm looking at academic code. Often researchers make the mistake of thinking, I'm coding this piece of software to do this simulation or this data analysis, and they think, I'll solve the problem myself, but when it actually comes down to it, there's actually a lot of other people who have actually solved that problem already, perhaps in a library or so on and so forth. So they end up solving a problem that's already been solved. And even if the problem isn't exactly the same, they could look to at least see how those other libraries and other code bases have solved the problem and take inspiration from that, save them time. Difficult thing to impart to researchers about that. I think there's a mindset in academic institutions, especially with researchers, that wants to solve the problem, which is a good thing. But if it's already been solved, why should you? This one is really good, and I thoroughly recommend you do this when it comes to the group coursework. Plan, always plan. Have a good think about how it's going to work from the top down before you start coding from the bottom up. There's an instinct that I've had to fight myself when writing code is, right, let's get coding, we know what we need to do, let's just go and do it, and you develop it from the ground up and hope it's all going to work really well when you try and hook everything together at the end. And we found this with the group projects. When it comes to integration of the final aspects, it's very important for everyone to be clear what the plan actually is, what the interface is perhaps between the Java side, the JavaScript side, and the Python side, for example. How those two are going to relate. So think top down, draw out architectural block diagrams, how everything's going to work, would be a suggestion. Solves the problem that it's meant to. As a developer, it's really, and especially also as a computer scientist, it's really fun to think, oh, this is great. I've already solved these problems, right, which are part of the goals of the project. I'll just go and do these as well, make it really cool and funky, and add these really nice features that would be really, really, snazzy and cool. But that obviously leads to more code, which can make code harder to maintain, harder to understand, and it means that you've got more to do if you need to change it later on, quite often. This one is incredibly important when it comes to research software. So if you have some software that's been written by a researcher and they publish the results of using that software in, for example, research publication, a paper, it's becoming more and more important for that software to be accessible by other researchers so they can reproduce the results of an experiment. So being able to make others replicate what you've done with software can be very important. So just on its own, if you can write some code and do it well, and other people can easily get hold of your code and replicate what you've done with minimal intervention from you as a chief developer, you've done a really good job. This one was quite weird and funny at the same time. Someone suggested putting funny Easter eggs in the comments. Go for entertainment, why not? Those can be terrifically boring. Well, the purists would probably say, no, you don't want to do that. No, that's just a waste of time. I don't know. I've seen some pretty funny Easter eggs in comments in code sometimes. We'll see one later. So what do other people say? Well, there's this blogger, Paul Elasher, on the MSDN magazine, all the way back in 2004, crikey. And you'll notice that a lot of the things that he said actually fall into line with what you said as a group. So, simple, readable, modular, layered, well, we said good architecture, should be designed, and we've already seen this point before. Thoughts are cheaper than debugging, so if you want to fix something, fix it early. Fix it in the design phase, as opposed to fixing it later on. It should be efficient, fast, compact, takes only what's needed, and frees all those resources when it's done with them. So we'll see a point on that later, on efficiency. Elegant. Someone also said from this group, elegant. Code should be elegant. Should be simple, efficient, and brilliant. It's not always easy to write brilliant code, but when you can, an elegant solution is often much easier to understand for other people. Although you should be careful not to make it too clever and too elegant, and to such an extent that obfuscates what you're actually trying to do. I think it's nice, recursive, beautiful, elegant recursive code that is horrendously hard to understand how it works, when actually a more iterative solution, as opposed to a recursive solution, would be clearer. But that's down to the judgment of the individual. Should be clear, of course. And being a realist, Paul says, clever hacks. The world isn't perfect. So when you come to write code, sometimes you do need to get your hands dirty and write something that's a hack. Perhaps you're trying to circumvent an error that you know exists in the library. But when you do so, you should try and do it in a clever way, so it's not too unreadable by others. Oh, a good point he does make also is readability is often neglected, but one thing to remember is source code, whilst it's consumed by computers, it is read, updated and changed by us. So source code is for people really, as well as machines. Christopher Diggins, he wrote a good article on properties of code, well, a very short article, on properties of code back in 2005. You'll see again that it reflects a lot of what we've already said. He also adds a couple of other things that I think are interesting. Can be easily understood by programmers without experience in your language. That's a tricky one. I don't think that's always possible. Depends on the language. Doesn't require much thinking to understand. Very little coupling. So as opposed to having horrendous sets of modules and libraries, and the coupling of all these aspects together is horrendously complex, try and keep it simple. That's kind of the antithesis of monolithic code, I suppose, but I think it's important to reach a good balance between the two. What else did he say that's interesting? Oh yeah, right. Makes just as much sense to you 1 year from now as it does now. I wrote a piece of code which embodied what I did in my PhD thesis. And I went back and looked at it about a year later, and I just could not understand what the hell I did. I regret that now. But hey, it happens. And he sums up all of these in one interesting sentence. He says, all of these properties I feel could be summed up simply as good code is reusable. And taking a step further, really good code is so simple can be reused by a trained skill. That's going back to what we said before about replicatability and reproducibility. There's also a blogger, Bitterman Andy, and he says a lot of these are trade-offs. You have to decide which ones are more important depending on the project that you're actually doing. So for example, you as a developer on a project, you often have only a limited amount of time to do everything, but you have to decide which ones are the most important given the project and what its goals are and what you're trying to do with the project. And I suspect doing a group project, that's something that will come into play. You have to decide which ones are going to give you the best trade-off when it comes to demonstrating your code. So that's what some people thought about what makes good code good, but looking at a bigger picture, there's 5 things you might want to consider when writing the code. This is not instructions for the coursework, but there may be some things in here you might want to take into consideration when you come to do it. One I've already said is make sure you get your requirements right. Understand what it is you're trying to do. We've already said that there's this order of magnitude difficulty increases, things actually as you move from design, requirements to design, through to deployments. Make sure you address those kinds of issues beforehand. This is the Galileo probe, which was launched into space, so it's a little difficult to fix bugs, not impossible, oddly, but a little more difficult. 1989 to 2003, 22,000 lines of code. Now, this was developed by what you might consider to be professionals. It had 122 software errors, known software errors, at the time, I think it was at the time it was launched. And 79% of those were because of the poor understanding of what was actually required. Think about that for a minute. So another thing you might want to think about is when you're writing code, I think we've alluded to this before, write code assuming that others are going to see it. And that could be a future version of yourself, other developers, etc. Always think about other people are going to read this code. This makes you, as a mindset, a better developer. Because it'll always make sure, you actually find your code will be better. As opposed to, let's make it work, then we clear up later. Then we come to the clear up phase, the refactoring phase, you perhaps run out of time. You've got a functioning product. Why would you want to spend more time doing that? But if you do it early, then you'll find you have better code. We've already said about comments. There was an example in a paper written in 2013 where they did an analysis of a scientific domain, which was species distribution modelling. And there was a popular algorithm that was being used to generate results, and all of these results ended up in lots and lots and lots of papers that were published. And they went to actually ask the people who had used this software what they thought of the code. But there were many, many people who just weren't even able to interpret what the original algorithms were trying to do. And they couldn't even understand how they were implemented in the code. So think about that. They were using code they didn't fully understand to generate results that were going into research publications. But they didn't understand how the algorithms work. Yes, it's harder to recode than it is to write it. So when you write it, make it easy to read. And this is something I think is really good advice. Donald Knuth said this. It was originally attributed to, I can't remember his name, T. Hoare in 1974. So Donald said, premature optimization is the root of all evil. So when you come to write your code, there's a tendency as a computer scientist and even as a developer to try and optimize it as you're writing it to make it the most efficient it can possibly be. But actually that's not always the best thing to do. That's often a trade-off between optimization and readability. And there are 3 rules of optimization which I really like. There's one that says, the first rule is when you come to optimize code, don't optimize it. The second rule of optimization is don't yet. And then the third rule of optimizing your code is don't optimize it until you've actually determined where the bottlenecks are. You can waste a lot of time on optimization as opposed to actually filling the function of the software. And that often makes it more unreadable. And yes, documenting the software is a good one too. So actually saying how the software works, we've covered this before, putting documentation into the code itself, perhaps writing a document that explains how it all fits together and how it works. Another thing you can do, and this is a general thing you might want to consider, this obviously I don't think would apply to the coursework because of the nature of it, but perhaps you can take away some aspects of it. Write code assuming that others are going to run it. So we've already seen that this morning, for every 20% increase in complexity, there's a 100 increase in the solution complexity. So things get a lot more complicated quite quickly when you start increasing the size of the problem space. To keep the problem simple, define the problem clearly and simply. And there's a few steps you can take to actually make it easier for people who actually want to run the code. So the first one you can do is to provide a build process automatically. So you can just say, I don't know, build.sh or something. And it goes away and does the build process for you automatically. And this makes it a lot easier, so when you actually come to, when you or someone else comes to make changes to the code, they can build the code very quickly and see if it still works. The build process is hugely complicated. It can really sort of turn people off trying to use your software and develop it and extend it. Another thing to do is to provide a test suite. So you provide a set of tests, unit tests. And each test might test some function in the code to check that it's giving the right results compared to the input. So, you made some changes. Let's see if they break anything that was actually working before. And you can keep these tests in there as the code develops, updating the tests as the code changes, adding more tests, refactoring old tests, so that someone can just quickly run these sets of tests over your code and understand whether it's actually functioning how it should do. And you can join these together. Once you have an automated build and test suite, what you end up with is something which is known as a fail-fast environment. So you are very quickly able to change the code, build it, test it, find out what went wrong, and then fix it quite quickly. And one for the real advanced well, something that's really quite advanced to do, is you can do things like nightly builds. So you have a server that's running all the time. It checks out the code from, say, GitHub repository, runs an automated build and test suite, and emails a report of what's actually happening to the developers every single night. So as the code changes during the day, you can still see if it works at night. And you go one step further than that, and you can use something called continuous integration. There's loads of free continuous integration services out there. What they do is when a set of changes has been made recently, it will check out the code, run a build and test, and then email you what the results are. Now, as I said, I don't think you need to consider that for the coursework, but it's something to consider when you go away and write other code that you're going to be writing for. We've already said, get others to look at your code. The first review and the first hour matter the most. When someone else is looking over your shoulder, seeing what you've written, and you're explaining it. And in fact, just the process of explaining how your code works can often uncover problems with it. And this was something that was found in a piece of code here. Commented out all this. What the hell was I thinking when I wrote this code? I've seen a few examples of that in other code. So you could argue that's an Easter egg, but it doesn't really give you a lot of confidence as to whether the code is actually going to be working the way it should be. So I think I asked the question a while back, who's used version control? And I think the majority of you said you'd use version control. So I'm going to ask that again. Who's actually used version control in any capacity? Perhaps just to check out some code from a repository and then just run it. Quick show of hands. Okay, alright. How many have actually used a code repository to commit changes to their code bases? Okay. So, yeah, so version control or revision control. So what it is really, there's a number of different models of how it works, but simply put, you have a centralized idea of what the actual code base actually is, and a history of how that code's developed over time. And this gives you some massive advantages. So it means that if you've got to a point in the code development cycle where you've perhaps made a big mistake in the code, you've committed these changes, you decide, oh my god, I made a huge error, I need to go back to where I was previously. Because the revision control systems have a development history of every single change that's been applied to the code, or at least concepts of changes, you can actually sort of check out a previous version that was working, and then just basically have that before you ever made any of those rather bad changes. It also means you can set up things like branches, so you can actually focus doing development of a new feature on a different branch to the main code base, which means that you're managing all those different feature changes in separate branches, and you can merge those branches back in to the main code base later on. So when it comes to doing things like collaborative development, you can have a number of people working on a number of different features on a code base. Each one could be doing that in a different branch of the revision control system. And a common question that we get asked is, what should you version control? And the answer is, as much as you can. Code, documentation, unit tests, test data, custom scripts you might need to do various tasks with the software. If you revision control as much as you can lockstep what's actually being developed. So if the code evolves, obviously documentation needs to change as well. So if you have, say, revision 10 of the software, and that's got code and docs, you update the code, and you want that to go into revision 11. But what you also do is update the documentation as well, and that goes into revision 11 too. So it's all in step. And you can have a procedure that actually makes sure that that actually happens. But you can have unit tests as well, so as your code changes, your unit tests change, how you test the software changes, that all goes into revision control as well. So when someone checks out the code, they have of a specific revision, a specific version of your software, they have the code, documentation, and unit tests they can run with that specific version of the code. And perhaps who's considered to be one of the best computer science teachers in the world right now, Greg Wilson, who runs Software Carpentry, he said, if you're not using version control or whatever else you might be doing with a computer, it's not science. And he directed that comment at researchers doing software development. There's a good reason for that, because if you can't reproduce the results of someone else's experiment, it's not reproducible, which means it isn't good science. Reproducibility is very much a cornerstone of science. And if you're using version control to generate the results, other researchers can get hold of your code, different versions of the code, and they publish different papers to do with it, and they check to see whether it actually gives them the results that you actually said were in the paper. So I won't go into this one in too much detail. A good example is GitHub, for example. This is a good revision control system that's out there at the moment. Code repository, you put your code in there, you have a change history, how everything changed in the code base. There's a number of support pages, you can do issue tracking with it, and you can release code quite straightforward using things like GitHub as well. And you can also add new members, new collaborators into it, into your repository of code, and then they can actually contribute changes as well. There are a number of ways you can do that. It makes it very easy for people to collaborate on code when lots of people are developing the same code base. I'm just going to throw this one in here. Something else you might want to consider, and I think this applies a lot to students, it certainly did to me. There's something which you might call crunch mode. So you've got a deadline, and you've got like 2 weeks to do it, you've got all this work to do, and you think, I'll just leave it till later. And you think, that's okay, I'll work loads and loads of hours, and I'll increase my output and make the deadline. It'll be fine, I'll just leave it a bit, it'll be fine. But there's been a number of studies that have shown this doesn't actually help you. So for example, going from 40, 60 plus hours in a week, they found that there was an initial increase in output, which was good, right? So you're doing okay to start with. But within about a week, you get a drop off, your performance goes down, your cognitive ability to actually process problems and solve them actually decreases, your output goes down, and then by 2 months in, you've been better off with just staying to a 40-hour week. So, something to consider. Wish I'd known that. So, what about the coursework? Well, there's something I want to draw your attention to on the Notewiki, and it says in the specification for the coursework, the contract will be awarded to the team that demonstrates the highest level of expertise in Python and JavaScript. And so how you do that is up to you. How you demonstrate how good you are as Python and JavaScript developers is up to you. But I'll just draw your attention to a couple of things. A well-designed system is 25% of the marks. How well designed it is, and well-written code, 25% of the marks. So it's up to you to decide which kinds of practices you should think about incorporating into the development of your group assignment software. So you've got 20 minutes to demonstrate the working system, but also you have a report as well. So think about how you will want to show these aspects, what are the best ways to do that. And so we talked about trade-offs with development practices as well. So which one should you adopt? That's up to you. Which ones do you think are the most important? Obviously you can't perhaps do absolutely everything you could possibly do, but think about how much effort you want to put into each one of them. So have a balance of the effort with the benefit of each of these practices, how it relates to your project. Have a think about that. Right, and finally, try to get good habits early and good advice. And it's easy to cling to bad ones. There was this article that was sent to a Usenet group, 1998. Someone made a comment, stereotyping Fortran programmers are somehow less likely than anyone else to learn something new, and unlikely to produce any insight. And someone responded to that with a Fortran comment that said, yes, I agree, I started out programming Fortran on a TOPS 10 system and other similar machines. Although I must admit, I still have some bad habits I picked up from the old days, but by and large I believe I've overcome the worst ones. There's some more there if you want to have a look, Python bad habits. And I think I'll close with that. So, right before we close, any questions? No? Okay, right, so the next lecture is going to be on Thursday, and that's going to be about Google App Engine. So, see how that goes. Okay, see you guys on Thursday.